Hi everyone, welcome to Linear Model with me, Sarini Abdullah. In this video, we will still be learning about multicollinearity, that is what is meant by multicollinearity, the consequence of having multicollinearity in our regression model, how to detect multicollinearity, and what should be done in the case that we have multicollinearity in our model. So, in the previous video, we already learned the mathematical reasoning and mathematical derivation of what happens to the estimated beta parameters in our model in the case that there is some multicollinearity. So we learned that multicollinearity give the consequences of unstable values of beta parameter in the sense that a slight changes value of the data results in quite big changes or a drastic change in the value of the estimated beta parameter. Now, in this session, we will try to illustrate that concept through visualization in the hope that it will be easier for us to understand that concept. So let's say we have a multiple linear model that is expected y, and in this illustration, we will just use two predictor variables to make it simple. So they're represented by beta naught plus beta 1 x1 plus beta 2 x2. And then let's see here that let's say this circle represents the contribution of x1, the first predictor, in explaining y, or in the form of this equation, that is the magnitude or the value of beta 1. Okay, now let's add the second predictor, that is x2. So in here we can also see that the circle, now represented by the green circle here, represents the contribution of the second predictor in explaining y. So then we can say that, okay, for our model before, that is beta naught plus beta 1 x1 plus beta 2 x2, we can see that, okay, beta 1 is the magnitude, okay, the measure, the amount of this orange circle, and beta 2 here is representing the magnitude or the value or the representation or the measurement of this green circle here. So in the case of multicollinearity, before we say that multicollinearity is that there is a strong correlation between x1 and x2. The correlation is kind of like big in an absolute value. It means that they share a common information between these two variables. So when they are working together in a model, then in the case of multicollinearity, we have something in here that their intersection represents the common information that is contributed by both x1 and x2. While in the case of no multicollinearity, we can see that there is no intersection or no common information shared by these two variables. So in this sense, we can see that, okay, so what is the amount of beta 1 in the case of multicollinearity? Remember that when we have the model, expected y equals to beta naught plus beta 1 x1 plus beta 2 x2, we do the interpretation that beta 1 here is that the contribution of x1 in explaining y after considering or taking into account the contribution from all other predictors in the model. So in the case when there is a multicollinearity, although the contribution of x1 is, let's say, this much measured by the orange circle before, But since there is some common information with x2, then the contribution of x1 now is actually just this much. While when there is no multicollinearity, it's just still the same. The contribution of x1 is this much. Okay, so the contribution is masked by the effect of the other covariate that is correlated with x1 in this case. Same thing with evaluating the contribution of x2 in the model. With the same argument, we can say that beta 2 now is no longer measuring this whole information here. Instead, beta 2 is just sharing, that representing the contribution of x2 after considering or taking into account the information from x1. So the beta 2 that will be come out in the estimation of the beta parameters in the model is just measuring this much, while actually when there is no multicollinearity, then beta 2 is the whole thing in here. So in that case, we can see that that's why in this case, we can say that try to avoid the interpretation of x1 or the separate interpretation of x2 in the model when there is a multicollinearity, because we can see that we might surprise why the contribution is so small. That in my understanding, x2 should be contributing quite significantly in explaining why the response variable y. But then it is actually, if we see it from here, but due to the multicollinearity, then it probably in our model, the effect of x2 will become insignificant. The same also with the effect of x1. Okay, so that's the problem that we will have when there is some multicollinearity in our model. Now, using of the model is not just trying to get insight on the role of each parameter in the model, but probably we also want to do the prediction. In the case that we are doing prediction, then we want to predict the value of y, then we take the whole information, right? So then all this information will be taken into the calculation. The same thing with when there is no multicollinearity, we also have something like this. And in this case, we don't really care how much is the contribution of x1, how much is the contribution on x2. As long as the whole contribution is taken into account in the model, we get the end result and that's it. So it means that if we want just to do prediction, and we don't really mind about the partial contribution for each predictor. We just take the whole thing from the whole predictors in the model. Then there is no problem with having multicollinearity in our model. So in short, we can say that when multicollinearity exists, try to avoid separate or partial interpretation of beta g that representing the contribution of each of the variable in explaining y. Still, we can use the model to do the prediction. There's no problem with prediction when having multicollinearity in the model.